Hello, everyone. Let's get started. Welcome, everyone, to join today's CGD seminar. I'm Jianzhu, host of today's session. Today, I'm very delighted to introduce Ufuk Turuncoglu. Okay, great, thanks. Yeah, Ufuk is our colleague at CGD. He's a senior software engineer. And he has a background in meteorological engineering, atmospheric and ocean sciences, as well as computational science and engineering. He has numerous publications and teaching experience in those fields. His primary research interests include computational simulation of Earth system components, air-sea interactions, lake hydrodynamics, scientific visualization using in situ techniques, and process automation through scientific workflow systems. His work also extends to climate science and dynamic downscaling. Ufuk is also interested in the design and development of fully coupled regional and global Earth system models. He is currently involved in several model development efforts, including the Unified Forecast System, the weather model, and the UFS coastal. The title of today's talk is Accelerating Earth System Modeling by Leveraging a Standardized Coupling Framework for Hybrid Physics Machine Learning Models. So during the seminar, please hold your question until the Q&A session at the end of the talk. And for people who are watching on YouTube, please type in your questions on Slido. So go to slido.com and use the code CGD seminar. With that, Ufuk, the floor is yours.
Yeah. Oops. Yeah, I think it's fine. Yeah, thank you for your invitation and then giving me a chance to talk today. Yeah, I was thinking about these topics such a long time, and then waiting for someone to come and then bring some funding. It didn't go well, so I decided to go and implement it in my free time, of course. I will start with my talk with some background information, and then I will talk a little bit about the hybrid physics ML-based coupled modeling approach, because if you say hybrid means different to different groups and different people. So there are lots of challenges over there. So to overcome those challenges, we introduced a new ESMF no-OPSI-based component called GeoGate. I will talk a little bit about that one. So it provides lots of different flexibility and features. And for this work, we would like to go with the Aurora foundational model. It's a machine learning-based weather model. And then I will present two fully coupled applications, both of them realistic applications. One of them is regional ROMS, regional ocean model coupled with the Aurora. Another one is the global S2S type application. So we are running 35 days. And then, again, it's very realistic configurations. Yeah, this graph basically explains everything in terms of the push related with the machine learning. And don't worry about the scale in here. They are always showing that those models are better than the traditional physics-based models. But this is just a single metric, upper atmosphere. Who knows what's happening other part of atmospheric situation. So, but the main thing is that lots of different models coming out, they are getting more and more sophisticated, using different techniques, and then they are getting more in terms of if you compare with the physics-based model, they are getting more accurate. But they have also issues. So there are lots of emerging challenges over there. For example, they are having some trouble to represent the extreme events. So they can predict the hurricane tracks, but they are always having difficulties to predict the minimum pressure or maximum wind speed, all those kinds of things. Also, they don't have enough physical constraints. So model is running, producing output, maybe precipitation, etc., with the ensemble approach, but at the end of the day, they are not conserving the mass, energy, etc. If you want to do a long-term simulation, those are important, right? And the difficulties with extrapolating the situation. So they know the extreme events because we are giving them using error 5 reanalysis, or also they can use the observations to get that information, but they have small set of extreme events. So there's a small pool over there, and then it will be hard for them to learn from that small pool to extrapolate. And also they are having issues related with numerical stability. So for example, if you want to run it for a longer time with higher temporal resolution, etc., they are having some difficulties over there. So they are not perfect, but nothing is perfect. So that's fine. Yeah, the meaning of hybrid physics ML models is different for different, under different conditions. So for example, some people could tell you that ML corrected physics. So maybe they have some kinds of ML-based data assimilation system or pre or post-processing system to improve the initial conditions or to correct the model while it's running. Or ML-based subgrid scale parameterization that can be coupled with the physical model, and then maybe you will replace the existing radiation scheme with the ML-based scheme, and then it will improve the results in a higher computational efficiency. Or you can have complete data-driven ML model, for example, just like GraphCast, GenCast, Aurora. For example, at this point in the UFS weather, the NOAA is trying to push machine learning. They have machine learning model based on GraphCast, I think. So they are producing ensembles, but they are not interacting each other. So they have physics-based 10 ensemble, ML-based 10 ensemble, and then they are combining them together. So it's not fully hybrid approach at that point. But today, I just want to talk about the real coupling. So we have traditional ocean model. We have ML-based another component. It doesn't matter which component. So it could be weather model, it could be sea ice, it could be land, or something like that. So it's a generic approach. So it's not new, but for example, there are some examples that they are trying to combine the die core, the traditional die core, with the ML-based physics. So this will bring some kinds of a constraint to the system because they don't have those physical constraints. So they can talk each other, and then they can exchange the information. They have also the DA frameworks, for example, sea ice coupled. For example, they create a physical parameterization for sea ice and coupled with the model. And then they are doing those kinds of things. AI2 is also doing something similar. They are using slab ocean model coupled with the AI model. And then they are trying to do long-term simulation with that one. They are great, but if you look at them, they are not generic. So if you want to port one of those, I think it will take too much time. And also, I think it's good to have those kinds of specific application because they are exploring different ideas over there, and then they can be easily ported to machine learning model, and then maybe it will help to improve them. So in here, our motivation is to leverage the strength from both approach. So we have machine learning, it's running, they are not perfect. We have traditional model, they are running, they are not perfect. So we are trying to find a combination that works better. This could help to improve the overall model accuracy, stability, and computational efficiency, because those machine learning models is much more cost effective. And by this way, if you have a way to couple them together in a generic way, you can create an Earth system model, or you can just modify your existing one. It will open a new way for you to do science, which is much more important. So this is just a tool. It's the dummy tool. So if you are not doing science with that one, and then there is no any meaning over there. So the scientific innovation is the main driver to bring this new capability. So we have two different worlds in here. One is working in Python, and mostly using PyTorch. They can access to GPU without any issue. Another side, we have Fortran or C, C++ traditional models. So two different words, two different language. They don't know, they can't talk each other. So we need something in the middle to translate the information between these two different worlds. So at that point, a new component called GeoGate could help, because it's a standard ESMF no-APSI component. And most of the models that we are using at this point, including CSM, UFS weather model, they are ESMF no-APSI based. So if you have a component that could interact with the Python, and it could have a standard interface to interact with all those existing models, then that will be the ideal solution, because then you don't need to worry about other complexities. It will be something like an existing model component for you, because other components doesn't know anything about who is sending that data. It could be machine learning, it could be real prognostic component. So the GeoGate is basically very similar to mediator, but it's not a mediator. So it can connect multiple components in the same time and then ingest data from them. So for example, you could have a machine learning model that could require different inputs from different components. That's possible. And it just mirrors their grid and mesh, and then it will ingest the data. And then through its plugins, you can reroute that information to somewhere. It could be machine learning tool, it could be something else. For example, even we are supporting the in-situ visualization at this point. Or you can bring your own plugin. Maybe you are not happy with the existing plugin. Maybe you want to implement something with FTorch or something like that, right? Or maybe you have a Julia component, you want to run it, but you don't want to create an external ESMF no-APSI wrapper around Julia. That's also possible. You can bring your own plugin, and then you can make it available. The design basically relies on that plugin approach. So because of that, it's extensible. You don't need to write the component entirely. You just need to write your plugin. It could be C++, C, Fortran, anything possible over there. So we have import and export state, just like standard ESMF no-APSI component. And we can interact with other components. And then we have a wrapper layer over there. It's written a specific library called Conduit, which is developed by Los Alamos National Lab. The purpose of this library to create a standard way to interact with different programming language. So you can interact with Python, you can interact with C++, you can interact with Fortran with its API, and you can create nodes, and then you can create structures, and then you can transfer the data. You don't need to worry about language barrier. So since we have that wrapper layer, we can interact with Python, we can interact with other tools. For example, Paraview Catalyst is also capable to interact with the conduit, so it understands conduit format. So you don't need to do anything. If you convert your data to conduit format, it will also work with the Paraview Catalyst. So there are lots of possibilities over there. So you can have lots of different use cases. You can support model development. You can do instant visualization, co-processing, language interoperability over there. But today, I am just talking about interacting with the AI/ML models. So in the development, I am always starting from simple. So no any active component, nothing exists over there. But the beauty of the implementation is in here, you could have multiple instances of the same component. So for example, same GeoGate component with two different purposes. One is atmospheric model, as an atmospheric model, so as a producer. Another one is the consumer. Because we can use different phase for a different application. So in this case, the atmospheric model, the fake atmospheric model, is sending some information to other component, and other component is doing instant visualization. And the atmospheric model, in this case, if you can see, we are creating some kinds of artificial data using Area 5 grid in the top plot. In the middle one, we are running GraphCast, small. And the last one is GraphCast operational higher resolution, using new NVIDIA Earth to Studio because it's easy to run. You don't need to worry about training, etc. So this gives you some flexibility because it doesn't need to be NVIDIA Earth to Studio. It could be anything. So you can write your own Python script to generate the data. Most of the ML-based models are not capable to couple because they are only producing small set of variables. Surface wind, temperature, maybe precipitation, and some upper level atmospheric variables. So it's not enough. We need humidity, we need flux, right? So to have real interaction with those traditional models. And also they are generally running in a low resolution. So 0.25 degrees currently is the common one. And the temporal resolution is also low. 6 hour, 12 hour. So, but we are talking about area hour or something like that in the real coupled application. For example, in the ROMS application, I am using 60 seconds. And mostly designed to predict only atmospheric state. So, of course, there are some individual research outside over there. They are trying to apply for hydrological process, sea ice, other things. But those mainstream models are only predicting the atmospheric state. So you need to bring those extra variables to the model. So that's the only way to do it is to train the model from scratch. Or like the Aurora model allow you to fine-tune the model. They train the model with the entire Area 5. If you want to bring extra variables, you don't need to train from scratch. You can just train for certain interval, for example, 5 years, 6 years. You can fine-tune the model, and then you can make available new variables. That's the beauty, because then it will be much more easy for us, at least for testing, right? So initially trained for atmosphere, but it's also fine-tuned using the transfer learning, and it's also used by the wave modeling, and it's also used by the chemistry. And they are getting pretty nice results with those. And also the main thing is that I could able to get some support, because if you create an issue in the GraphCast or something like that, those Google engineers are always busy, and then it will take age to get some answer. Okay, why this variable is not exist? Wait two months, and then you will get answer. Okay, sorry about that. So but I could able to get some support from Wessel. He's working in Netherlands. He's one of the main author of the Aurora model. So he's a very nice guy, helping me about my dummy questions. So Aurora models, extendable, that's great. So it's great to use. So this is the this is some results from our fine-tuned model. Because the fine-tuned model, we have relative humidity, sea surface temperature, precipitation, short wavenet, long wavenet, and downwelling components. So this is a subset that we can use to drive the traditional physics-based model in a realistic way. Of course, you can add more variables if there's missing. It's easy to train, so we have way to train at this point. And we are getting pretty nice results, especially for a couple of days. Of course, we know that those models are not good, especially for the long-term simulations. But that's fine. We are not trying to make them perfect, right? We are just getting them, modifying them for our purpose to test some idea in here. And we are getting relatively close RMSE and correlation values with the weather bench 2, which is good. And also, we found out that including new variables is also improving the model results. So you can see the surface and the upper atmosphere over there, especially in the warm seasons, spring and summer. The new variables is basically reducing the root mean square error of certain variables. We have some issues with the temperature, but we are thinking that this is basically related with, we are adding new variables, and the model is trying to create a connection between all those surface variables, and then it's make hard for it. Because we are training the model for 6 years or something like that at this point. So if you have a longer time training, if you adjust the weights in the loss function, etc., I think we can still improve the model more. But that's fine for us, because this version can be usable to drive the existing traditional models. Yeah, I already told about that. So we are in the range in terms of the performance of the ML-based model. So the first realistic application in here is the regional. This is coming from one of the standard tests from ROM's repository. So Hurricane Irene, we are trying to predict the Hurricane Irene with this model. We are not trying to predict because our simulation range is 42 hours, but we are trying to force the ocean model while the hurricane is passing from that region. So a little bit more information about the Aurora performance in here. So we did lots of different utilization. We start the model from different dates. The black line is the Era 5. The red one is the best track. So as you can see, Aurora is in the range. So it's predicted to track pretty well. But if you look at the minimums, mean sea level pressure and maximum wind speed, it's not good. That's normal because those models have always issues with those extremes. Even GraphCast, other models. If you look at the Era 5 is also have a large bias over there. So if you train the model with Era 5 that is already have a bias over there, then it's normal to have the bias in your ML model. That's fine because it's known issues. But maybe in the next release, they will solve those issues and then it will behave better, right? That's the scientific progress. In terms of total precipitation, because precipitation is important for us because hurricane brings lots of precipitation, we have a satellite-based observation over there, CMORPH, and the green area is the ROM's grid. satellite-based data, ERA 5 and Aurora. Aurora, the position of the maximum precipitation is captured pretty accurate. But the intensity could be a little bit low because it's low resolution. And also you can see the data prediction in here with different dates. We have a circle, and then we calculate the average over that circle. And then we create the time series. So based on that time series, in the first lead time, Aurora seems better than ERA 5. But if you increase that lead time, 12 hour, 16 hour, if you go like that, and then its performance is reducing. By the way, Aurora, the original version of Aurora, doesn't include precipitation. We just trained the Aurora 6 years with the precipitation. So if you train longer time, probably you will get better results. So how it looks like in terms of the design. So in the left side, we have an application, CDEPs used by CSM2, and ROMs, regional ocean model. We are driving with ESMX driver. We are not driving with the CSM driver or UFS driver to get rid of that complexity. And then in the right side, we just replace CDEPs with GeoGate plus Aurora. Because if you want to interact with the ML model, you need GeoGate. And then the run sequences are pretty similar, except we are running specific phase to interact with the Python over there. So if you have a different plugin, you can define your own phase, and then you can trigger that phase with the run sequence. You could also trigger multiple phase. So first interact with Python, then interact with Julia, and interact with something else, co-processing. That's also possible. These are the set of simulation that we did with this regional. So we have 4 different CDEPs force simulation, and we have also 2 Aurora force simulation over there. R3 and R5 is the comparable ones, because R6 is using 2-way interaction, because CDEPs doesn't allow you to get the sea surface temperature from the ocean to calculate the fluxes, etc. It's a dummy data component. But Aurora is able to interact. So we can feed Aurora with the SSD data produced by the active physical model. There is no any limitation over there. You can include lots of different variables to interact with other models. It's just based on your training. So if you train, if you add those new variables, you can fit them. Yeah, we select lots of in-situ observations over there. So we have stations and their locations over there. And then we are just trying to look at the different components of the solar radiation over there. I think this is the short wave, downwelling short wave. Another one is the long wave. So the Aurora is in the range. So it's producing a similar output like ERA 5 at this point. Another thing is that we also check the wind direction and wind speed, because it's important, especially for the hurricanes. So we have different runs over there with different colors, and we have observation blue. As you can see, our RMSC and in terms of the direction and speed, the Aurora is doing pretty good job over there when it's compared with the observation, and also you can compare with the ERA 5. Yeah, this is the much more, there are lots of information in here about atmospheric temperature, the surface, near surface temperature, I think, pressure, wind direction, wind speed, and water temperature over there. We are comparing different stations, and we are calculating RMSE and correlation coefficients. And it's always in the range with the ERA 5. Sometimes it's better, sometimes it's getting slightly worse, but it's in the range. That's a good thing. If you look at the spatial distribution of sea surface temperature average over the entire simulation period, so we have satellites observation over there, the first plot, and then the others are the difference for the different simulations. We are seeing some kinds of a cold bias over there, especially in the near the coast. But I think that's related with the hurricane, because hurricane comes and then creating an upwelling over there. It brings lots of cooling, and then because of that we have a cold bias. So I think that the satellite observation at this point has some kinds of an issue, especially it will having a hard time to see the ocean because we have a hurricane over there. But as you can see, the Aurora forced simulations producing similar cooling effect with the ERA 5 forced one. So the results show that we have a pretty good performance when it's compared with ERA 5. Lower RMSE, higher correlation than ERA 5 in some cases. We couldn't see any significant sensitivity to sea surface temperature in this simulation because it's pretty short, 42 hours. And also, we are feeding the underlying ocean model with 6-hourly data. Of course, we are doing some kinds of linear interpolation over there to match with the coupling interval. But at the end of the day, it's 6-hourly. So if you have a machine learning model that creates higher temporal resolution information, then you can see the effect of that feedback much more easily. So the second realistic application, which is much more interesting, because at this point, we are using one of the regression tests exists in the UFS weather model. Data atmosphere coupled simulation. It has two different model components, ocean MOM6 global and sea ice global, including sea maps and sea depths. So it's much more realistic configuration used for S2S type forecast. Yeah, I was interacting lots with Dennis and Nick related with some issues in the initial condition because the regression test is basically designed for different dates, but I was planning to run for different dates. So I got initial condition and then I make it work for 2021. I am starting to run with different seasons for 35 days to see the performance in different seasons. Again, the structure of the modeling system is very similar. ESMX driver, we have actual configuration in here. In terms of the actual configuration, we are just replacing the sea depths with the GeoGate and the Aurora. But there is no any restriction. You can remove Aurora from there and then you can bring your own. That's also possible. And different experiment again. So sea depths forced, and we have two different Aurora forced simulation for each season. So in total, we have 12 different simulations. And we compare the results with the ERA 5 and then available observations. So in terms of sea surface temperature distribution, we compare with the optimal interpolation sea surface temperature. Of course, we have higher resolution sea surface temperature data, but it's not necessary, I think, for this case because it's already 0.25 degree or something like that. So we have ERA 5 forced simulation, Aurora forced, and the two-way coupling with the Aurora. They are very similar. So we have some warm bias in the Arctic region, but that's coming from the model configuration. It's not related with the data atmosphere or it's not related with the Aurora. So we have some issue with the initialization of the model. Plus, I think the configuration of the model is not designed well. Plus, based on my this discussion with Dave, using the data component with the ICE model is not producing good results because then you don't have two-way interaction with the ICE. But that's fine. We are not trying to solve all the problem in the same time. If you look at the graph in the right, the blue means, the red means the Aurora is producing lower RMSE, higher correlation. So at this point, for different seasons, for different regions, for example, we have different regions over there. Nino regions is especially important for the predicting La Nina, El Nino events. We have also global and regional oceans over there. So they are pretty close. So it's good because I was expecting that, okay, maybe I will have some kinds of stability issues and the model will crash or something like that. But it's forcing the underlying physical components without any issue related with stability. That means that this model is somehow creating a consistent data, right? Because if there is a long interaction or long link between the different variables, for example, humidities, short wave radiation, etc., then model will go crazy, right? But it's working fine. So if you look at the sea surface temperature coming from MOM6 for different regions, for different seasons, the RMSE values are very close to ERA 5 forced one, including the observation. So we are doing pretty good job with the Aurora simulations for different regions. What about the difference between the one-way coupled and two-way coupled machine learning configuration? If you look at the Aurora, the one-way coupled simulation and the difference between the one-way and two-way. So we are having some level of difference over there. Of course, you need to go and you need to look at in a detailed way to understand why. But the main difference between two configurations is that the MOM6 basically produced that as sea surface temperature data and sending to Aurora. Aurora using that sea surface temperature data rather than using the ERA 5 provided one. So that's the difference. The one-way coupled using ERA 5 SSD, another one is using MOM6 provided sea surface temperature data. We have lots of difference over lots of variability over the current region over there. So yeah, again, you need to look at, for example, we have lots of data over there that needs to be analyzed. So you can look at 3D cross sections, you can look at different things. But for first paper, I think this detail is enough in terms of showing the performance of the model in terms of coupling with the traditional model. Again, sea ice, we have two different observations over there. One is coming from the optical interpolation sea surface temperature. That also includes the ice coverage. And other one is also coming from the satellite observation, the black one and the blue one. So as you can see, the model is predicting pretty well, except warm seasons, because we know issue over there because we have warm bias. It could be the initialization issue, or it could be related to the model configuration. I have new test, but I couldn't find time to process the information coming from there. The ice extent, the ice extent is fine, and the ice coverage is also predicted pretty well, at least in the range with the data atmosphere coupled simulation. That's the important thing, because we are trying to replicate that simulation. And we also know there are some issues with ERA 5 data in terms of the representation of the surface air temperature. I found a couple of sources over there. You can go and check. So most of those AI ML based models are trained with ERA 5. So they are assuming that ERA 5 is the best and producing very close to observation, but it's not. So ERA 5 has lots of issues. So since you are training your model with those issues, you are inheriting lots of things. And then you don't know those things. So it's better to, maybe in the future, they will purely train the models with observational data. That will be best. But at this point, we need to go with this way. As a summary, we have two different configurations. One is regional, one is global. They are using different components. But they are using same architecture to couple with the machine learning-based models. And then we demonstrate that they are working fine. So of course, we have some issues with the results, but those are also exist in the data coupled configurations. But there are lots of room for improvement. Plus, maybe you have a better model, machine learning model, just for climate type simulations or just for a specific process or something like that. We can try it. So it won't take too much time for us to have initial run. So that's good thing. So you can start experimenting something in here. So what's next? So you can use your homegrown ML-based models. For example, KM emulator could be an option. You can start to test some ideas. So this could be a nice way to test the performance of the existing machine learning models. So just like weather bench, maybe we can create a standard testing environment, standard coupled configurations, and we can ask others to bring their own machine learning models to force that configuration with their models, and then we can check the difference between them. So that would be super interesting, I think. You can do bias correction, data assimilation. The existing infrastructure allow all those things. The GeoGate component is already part of UFS Coastal. We will use for different purpose. We will process the data on the fly to create S products for them, but there is no any restriction, so we can push that development to upper level, the UFS weather model, and then we can start using over there. At least we can try to experiment. Especially for UFS Coastal and HAFs, it's important because they are doing short-term prediction with some extreme events. We know that the track is predicted pretty well with this model, but they could also have their own model. So what happens if you could able to create multiple ensemble with this AI ML model? So we can create multiple ensemble, we can average them, and then we can feed other models with that average. Or we can have multiple instances. So there is no any limitation. So endless possibilities over there. We have still room for optimization especially in the component side. The Python initialization cost. My observation is that we have some kinds of a cost in the initialization, but we can solve it. I think we need a better software engineer to look at that layer, because I am not expert in mixed type programming or something like that. So I am just good in reverse engineering. That's all. Yeah, the Aurora model can be also improved, but yeah, that's not the only model that you can use at this point. Yeah, I think I can get some question if you have. I think I am pretty good in terms of timing. Thank you.
Thank you, Ufuk, for the exciting talk, and thank you for introducing us to this exciting new framework. Any questions? Katie.
No, thanks for your talk. You mentioned it briefly at the beginning, but what's the difference between GeoGate and FTorch?
FTorch is just a way to run the PyTorch models. If you are using, for example, let's assume that you have a physics subgrid scale parameterization. You want to ingest it in your model, so you can use FTorch. But it's just as specific to that application. But with this application, we are directly interacting with Python. So then it will be much more easier for the user to bring their own Python script, and then they can start experimenting something over there. there's not too much difference over there, but that's just a way to trigger your model. So if you want to go that way, we could try the plugin, and then we can trigger the model like that. Maybe it will be much more efficient, I don't know.
Bill?
Yeah, thanks a lot. This is really neat to see, Ufuk. Maybe somewhat similar question, but in a little different direction. It seems like this is filling the need that we had talked about in the ESMF team to put in place like a C++ and a Python interfaces to models. It seems like a big advantage, a big thing that you're getting out of the GeoGate is that you're providing that. I guess sort of a question for you and the others in the ESMF team in front of me here, like are you envisioning this as a longer term path forward? Is there still kind of consideration about having a C++ and Python interface to ESMF? And if there was a C++ and Python interface to ESMF, would that satisfy a lot of the needs of GeoGate?
I think, of course, having a native C++ support, fully supported with the no-ops layer will be great, because then you don't need to worry about the Fortran. You can get rid of Fortran, and then you can bring your C++ wrapper layer, and then you can go with that one. That's perfect. But I think at the end of the day, nothing will change. So you still need to have GeoGate. Maybe it won't be written in Fortran, but it will be written in C++. Because you still need to interact with the Python, you still need to have a standard way, ESMF no-ops layer, right? You can create ESMF no-ops layer outside of your Python script at this point. But maybe in the future it will be possible. But still you need that component. It's written in Fortran or it's written in C++. It doesn't matter. But you need that component at this level. Of course, if you have a funding, if you have a long-term commitment, then you can go with writing your no-ops script in Python.
If I can add another layer, like as Ufuk has said earlier, GeoGate is really good for rapid experiments, right? So if you already come with an existing model that you want to try to interact with another physical-based existing model, GeoGate is a perfect tool for you to use. And I think Ufuk had demonstrated some realistic application that he had demonstrated that it's feasible.
This is
the CAPI, yeah.
Yeah, this is the only way that we can push our boundaries. So this will give you a capability to start testing now. Of course, you can go somewhere else and then you can do it more efficient way or optimized way. But it will take time for us. So until that point, it will be nice to go with this approach.
Yeah, thanks.
Yeah, that's it. The CAPI route, we're still actively looking for funding, so anybody who's looking for
Funding!
plug in, shamelessly. But, like, again, GeoGate to me is like rapid prototyping. You can try it, making sure it works, and then you can commit into making something that's part of, specifically for another ecosystem like CSM or...
Maybe you won't get good results and then you don't need to spend money, right? But maybe if you go with this route and then you will get nice results and then you will think about, okay, let's optimize this one, make it more efficient. Maybe then you can find money and then you can go with that way.
Great.
Thanks.
Yeah, this is, I'm really glad you got this put together because this is a capability I've been looking for AI emulator coupling. I guess the question is, do you have any plans to start working with, I'd like to work with you on getting credit stuff integrated into this. Since we built Camulator to explicitly have all the things you're listing and talk that Aurora doesn't have, we have that in Camulator. In terms of physical constraints and variables to actually couple with other parts of the Earth system. So
I think that will be great.
Yeah, we should follow up.
Yeah.
Just a quick reminder for people who are watching on YouTube. If you have questions, please go to slido.com and type in your questions. I use the code CGD seminar.
Yeah, Ufuk, since you had a version, I think it was of the S2S, with the data component and then a one-way version and a two-way version, did you look at the overhead and performance and the scalability of those? Did it
In terms of performance, CDEPS is better.
Okay, right.
But because of the initialization cost.
Right, okay, so it's mostly the initialization, it's not the runtime?
No, yeah.
Okay, interesting.
And also we are running on GPU, so
Right.
you can run, if you have a model runs multiple GPU, multiple nodes, we can support that one too.
Great.
So the only thing is that the initialization cost. So yeah, we can, of course, yeah. Maybe there's someone out there smarter than me and then help me because yeah, I think this is a teamwork. So the infrastructure over there, but yeah, so better ideas will bring optimization, will bring better results, I think.
Great, thanks.
So I don't think you mentioned what resolutions you're using in either the.
In the components or in the Aurora?
In the components.
Mhm.
Say in that coupled model, what resolution are you
I
using?
think it was 0.25 degree. Yeah. In both MOM6 and CIC is using same grid, 25 degree.
So,
And 0.25 degree.
so what I'm asking, is this a method to be able to use much higher ocean resolution and yet get the integrations in a reasonable amount of computer time?
In terms of the implementation, you just need to replace the configuration of the underlying ocean model. That's all. Because since you have an ESM maps layer, it's totally isolated from the other components. So the CMaps mediator will handle the interpolation between the components. And I think that was an existing configuration used by UFS Feather model. Because I didn't want to create the configuration from scratch. It's too much work. So just go and pick that configuration, try to run and then see the results. But definitely we can change the components, we can change their configuration, resolution, everything is possible at this point.
So if I may, are you asking if we have Camulator in there, can we spin up the ocean faster by using Camulator to provide atmospheric forcing and spin up the ocean? Is that what you were trying to get
I
at?
was thinking about, the Mesa Clip results have said that using a tenth of a degree ocean, quarter degree atmosphere are giving much better results than lower resolution ocean. So
Yeah.
I'm asking whether this is a method to be able to use, say, tenth of a degree ocean sea ice versions of our model to make it much cheaper than the traditional one.
To be honest, first I start with the CSM, C concept. But it was too hard for me because it was using data atmosphere, JRA 55. It was so hard to understand because at the end of the day, the NoAPC configuration file includes all the options. It was too complex even for me to understand what's going on over there. Which one is required, which one is not. So because of that, I know UFS Feather model. I went there and I picked that configuration. But it's also possible to use any configuration from CSM. Even we can integrate GeoGate with the CSM and then you can run, for example, C concept with Aurora or another model. That's also possible. Fred, do you still have a question?
Yeah, you mentioned Julia. There is a new wave model written in Julia. Will that GeoGate be like a way to bring it in CSM?
Yeah, we are part of that proposal at this point. We will see. So once it's funded, if it's funded, we will look at our options. We can use the same approach to bring that component. We don't need to use GeoGate, but we can use the same approach, having a conduit interface, C++ interaction, and then we can create a standalone component just for that application. Or we can create a new plugin in here, and then we can use any Julia model with that way. But we have a limited funding in that project, so we don't know at this point which way is the best. So we will see.
You mentioned that there is some pleasantly surprising stability. I was wondering if you tuned any of the coupled models. I guess just thinking about as soon as you couple an emulator, maybe you're moving it off its attractor, out of its training data. Did you encounter any difficulties there?
In my case, I didn't have any issues.
For example, the trained Aurora model is basically creating, for example, negative humidity or negative short-wave radiation or something like that. It was causing issue in the underlying model. But those kinds of things can be solved in the model level in a better way. So we have some options over there. But since we are doing some kinds of quick experimentation in here, I didn't go there and try to change anything in the model level. But that's also possible. There are lots of different ways to do it.
Let's take the online question first and then go back to the one. Can you elaborate on where the fluxes are calculated and how the AI atmospheric model use these fluxes?
For the regional case, the atmospheric model, the component, Aurora, is sending the atmospheric surface state, and TinyROMS is calculating the fluxes by using its own bulk flux format, just like data atmosphere. In the global configuration, atmosphere ocean fluxes is calculated by the mediator. So Aurora is sending data, other components they are sending their own data, and then mediator doing the calculation and sending the fluxes. At this point, we are not getting those fluxes from mediator to Aurora. But we can configure the Aurora to get those fluxes from the mediator to do the next prediction. That's also possible.
This is, I guess, on the technical side, like, what would be required to get GeoGate into CSM? Like, do we need newer version of ESMF? Do we need newer CMAPs?
I think the current version of ESMF will work without any issue. The only thing is that you need to create a specific Python environment for your needs. So for example, let's assume that CAM emulator, I don't know if it's written in Python, if it requires some spatial module or something like that, you need to design your Fortran module using that environment. That's the only limitation at this point in our end. Of course, if you want to use the inst visualization, etc., then you need to install those tools. But if you are just going to interact with Python, there is not too much limitation over there in terms of dependencies.
Very nice talk. I wanted to follow on from your question, your comment about how the fluxes are used in Aurora. So I think you said they are not used in Aurora.
The Aurora basically gets the fluxes from ERA 5. Fluxes means that the short-wave radiation, downwelling and net, long-wave radiation, downwelling and net. But we don't have, for example, latent heat, sensible heat flux, or any other variables calculated by receivers. But we can have much more tighter integration. So, for example, just think about the CAM. Which variables in CAM is provided by the mediator? If you know those variables, and then we can fine-tune Aurora to get the same variables, and then we can fit the Aurora with the same variables that we are using with the CAM interaction. Maybe we need some kinds of ice interaction, maybe sea ice concentration, etc. needs to be included to our model to define those two-way interactions. So yeah, there is no any limitation, and it's possible, totally.
Does it see the SST at all, or in Aurora? Does Aurora see the SST from NOM6?
That's the only variable at this point. But if you include more variable, maybe you will see more change in one-way and two-way.
Thank you.
Sure.
If there's no more question, I know because time constraint, you cut slide number 43 out, which is hybrid jobs, and then the resource control. Do you want to talk about that a little bit?
The hybrid kinds of things. Yeah, the CSL helped me to run those hybrid things. So the component, the GeoGate, doesn't know anything about what resource available over there, but Python knows the GPU available, and then it will pick that GPU, and then it is running over that GPU. But after that point, once we calculate the prediction, and then we are getting that data to GeoGate, and then GeoGate is sent to other components. Of course, GeoGate is running on CPU. Yeah.
Maybe one last question. Yeah.
So I'm curious about the scales, right? We use FTorch for replacing ML parameterizations, and you've demonstrated GeoGate for like the component scale integration. What about this like intermediate where I want to replace the vegetation model within CLM, but I want to run most of CLM? Is that something that GeoGate could handle?
There are multiple options over there. To be generic, I think you need to implement something in this CLM side. For example, you could have, for example, the component could have also it could have sub components. So, for example, the radiation scheme could be a no-opsy component, a land scheme could be another no-opsy component inside of the model. So once you have that separation, I think you can couple with this way. But we don't have that separation at this point in the CLM level. So maybe that's the best approach is go with another way. But that's possible. So if you have funding, we can implement those kinds of things. And even you can create ESMF no-opsy interface over CCPP. Then what happens? CCPP will be the standalone configuration. You can port it anywhere. And you can also run CCPP in a higher resolution than the host model. There are lots of possibilities over there, but yeah, again, at the end of the day, you need funding for those things.
Okay, in the interest of time, let's wrap up. Let's thank you for the
Thank you.
Thank you everyone for joining. Have a great rest of your day.